Alright, so yesterday I did this exercise. Write down an algorithm for finding the minimum or maximum of a list of numbers. Those of you who have programmed before may find this a good exercise as well. Why? Anyone know? Yes?
You're devising loops and stuff.
Yeah, well, we're looking at loops, but we need to separate. Yes? Sorry, I didn't quite hear you. I can't actually hear. Something in the structure. The data structure. No, that's exactly the point. We're not talking about data structures. Yes. Use this in sorting. Yes. No. Okay.
The exercise in pseudocode to go back, take a step back from our.
Okay, is that what you were going to say? Yeah, no, oh my God. Yes, that's. Yeah, well, the idea is, for those of you who have programmed before, I notice you're very tied to the idea of programming. The idea is to step back and look at the problem without the question, am I using an array? Don't worry if you haven't heard this before. It's not the right question here. We don't care what you're using. That's implementation. We're talking about the problem. What does implementation mean? In a computer science sense. Yes? Yeah, creating a version of it in a program. You implement the program. So we have an algorithm, and then you implement it. It's another way of saying programming. Creating an instance of it, in a way. Okay, so how will we write on this algorithm? What is the algorithm? Where do we start? Yes? Okay, and what happens if we have minus 6 million in the list?
No, I'm saying initially.
Okay, so we're looking for the minimum, and you say make minimum
Say make both of them
equal to 0,
Both of them zero.
but in the list we have minus 6 million. Will that work?
Yes, when
No, minimum's equal to, oh, sorry.
There is no list, only zero.
I'm saying initially though what you said.
Yes, but 0 is a bad idea, is what I'm trying to say. I'm being a bit silly. Let's say the minimum in the list is 6 million. Sorry, not minus 6 million. Say that's the lowest number. Yes.
Ma'am, of your list of numbers, you have to declare your lower and upper boundaries.
We're not declaring. Okay, what are you saying?
You have to state your lower and upper boundaries.
No, we don't have to state the lower and upper boundaries. It's the blue in the back. Yes, but we're just going to find one right now. So let's just find the minimum. I said or, not and there. Okay, so we're just going to find the minimum. Yes, that's a good suggestion. Yes. Well, that's what we're going to do to find the minimum. But where do we start? What do we say the minimum is? So the one question. Well, you could pick random, but first is just as good as random in this case. Yes.
You arrange the number from the smallest to the largest.
No, that's a sorting problem. That's harder. Arranging them from smallest to largest is actually harder than finding the minimum. It's a harder problem to solve.
Okay.
Okay. Yes. Okay, now just hang on. Let's just stop at step 1. I'm just checking step 1. Okay, yes. Yeah. Sorry, we're not XN, we're not talking that way right now. We're just talking about the problem. Okay, don't get tied to terminology. It's important exercise. Okay, so I just want to make clear here. The question when you start, there's one question that none of you have picked up on yet. There's a problem. Okay, but in my assumption, set the first value of the list to our current minimum. That's fine, except in one case. Sorry? That's fine, yes?
If the first value exists.
If the first value exists, what does that mean? What are you saying in English?
If there is a first value.
And when would there not be a first value?
When there is no value at all.
When there's no value at all, which is where there is an empty list. Okay.
Let's compile.
Yes. Yeah, okay. So we're going to say rubbishy lists we're not considering. We're defining our input. we're only looking at lists of numbers. Everything else is wrong. Okay? Your program needs to deal with that. So we're only looking at lists of numbers, but we can have lists that are empty. There are no numbers. Okay. So we need to make sure. So if the list is empty, what we do?
End program.
End program and hopefully say something. Not end program, it's not program. Stop and say there's a problem. Yeah.
Stop and say the problem, or you could just say if it is empty, put a whole lot of random numbers.
No, I think that would be bad. I think that would be bad. Think about when you're using this minimum function and you accidentally get it on in an empty list. Instead of throwing out something bad and an error, it's going to just keep working. Those are the worst kind of errors. They just keep working because they're hidden. And if you think that hidden errors are not a problem, do you guys remember some years ago the entire practically eastern seaboard of the United States had a blackout? No power for like 8 hours.
Yeah.
That was a software bug. Okay, quite a complex software bug. A data race it's called, but it was bug. Cost a lot of money. Billions. Okay. So software bugs can be a problem. Okay. So the issue here that I'm trying to make clear is that the idea is that you've got this storage space or like a place in your memory that you're remembering what the minimum is, but what you start with. And the first suggestion is a common suggestion that you think, oh well, the lowest, the highest you could get is 0, and maybe there's lower. But if you assume that you're going to set minimum to some value, call it 10, 100,000, you could still have a list of numbers that are bigger than that, and then your algorithm will not work. So the best suggestion is to set the minimum to one of the items in your list. You could choose a random number, but it doesn't make any difference whether you choose the first one or random, and random means you have to generate a random number to find a random position in the list. So we just pick the first one, and we set the minimum is equal to that. Okay, so what is the next step? Yes, Mr. Pink. Huh?
Look at the next number in the list and see if it's less than your current number.
Okay, so then we look at the next number in the list. What should we do if there's a next number? If there's not a next number in the list, what do?
That's all.
We output the minimum and we stop, which would be the first and only number in the list. If all the numbers are identical, it doesn't matter because they're all the minimum. So it doesn't matter if they're all 52, your minimum will be 52. That's just a question of looking at there. Okay, so what we do is we've set it to the first one. We see if we can move one on. If there are more numbers in the list, if they're not, then we stop and output our current minimum. Otherwise, we look at the next number and what do we do? Is it less than the current minimum? If it's less than the current minimum, then we reset the minimum. Then what do we do? We repeat it. We go back. We go look at the next number. Is there a next number? If there's not, go to the end. Yes. We're talking about numbers right now. We're assuming that we understand the basic operation less than. Yes. The algorithm, but most computers can compare numbers. If you're comparing something else like hamsters, okay, then you have to define what it means to be less than as a hamster. Is it less furry? Is it less fat? Okay, that kind of thing. But we're not talking about hamsters, we're just talking about numbers. Okay, so we keep on doing that. Check if there's another number. If there is another number, compare it with the current one. If the current one is bigger than that one, as in the next one is smaller, you swap it in, and then you keep going. Okay. Yes. Your name is Franklin. Yes.
From where do we before reading the first number or right now?
Okay. So it can vary. Depends how you define it. This is how I've defined it. Oh, sorry, I didn't put the step in there because I was automatically numbering. So let me just put it in. So if the list is empty, display an error message and go to step 8. Step 8 says stop. The next step, start at the beginning of the list. See, I'm not defining what the list, how it's stored, all that sort of thing. That's programming language dependent. I just said this is how you do it. Start at the beginning. Set the current minimum to the first number in the list. We know it's not empty because we checked the top. Okay? If there are no more numbers, display the current minimum and go to step 8. So this is a decision. Okay. If there are no more numbers, then display the current minimum and go to step 8, which is stop. But if there are more numbers, you'll move on to the next number in the list. If the current number is less than the current minimum, set the current minimum to the current number. That just basically means keep track of the minimum, and if your current number is less than it, update your current minimum. If you are frowning, then you need to ask a question. Okay. Then go to step 4. So this is our loop in my version of this. Okay. And we keep on doing this, and we only exit the loop when there are no more numbers. Okay. Any questions on this? So I'd like you to step through this algorithm with a list of numbers. For those of you, can you guys see here at all? We'll start with 5, 8, 2, 6, and 3. I'm doing this because it's quite important to mentally go through these things. So that's our list. If the list is empty, it's not empty. So we move on to the next step. Start at the beginning of the list. Beginning of the list is here. Okay? So we're here. Alright? Set the current minimum to the first number in the list. So we'll have a little storage space which we will call min. And we will put 5 into that storage space. Okay. If there are no more numbers, display the current minimum. Well, there are more numbers. So we're going to carry on. Move on to the next number in the list. So move on. That's 8. If the current number is less than the current minimum, is it?
No.
8 is not less than 5. So it's not. So we go on to the next step. Go to step 4. So go back to step 4. Are there no more numbers? No, there's still more numbers. Move to the next number in the list. Okay. If the current number is less than the current minimum, is it? The current number is 2. 2 is less than 5. Yes. So when we say yes it is, set the current minimum to the current number. 2. Go to step 4. Back to step 4. If there are no more numbers, well, there's still more numbers. So we then move on to 6. Compare 6 with 2. We don't change it because 2 is bigger than 6. And then we move on to, there are still numbers. We move on to the next one, 3 and 2. And then there are no more numbers in the list. Okay, so we move to step 8. We display it. Then is equal to 2. And we stop. That's called stepping through an algorithm. When you write an algorithm, you should take some values, examples, and step through it. Have I proved that this algorithm is correct? No. No, I haven't. If your car breaks, or you have a car, you've just bought a new car, second-hand because you're a student, and it's very old. Do you know that it has any problems if you've driven it once? So you drive it from the dealer back to your race, and you park it. You had a fine drive. It was great. Is your car proved free of fault?
So you'll never know that because it's also
You will never. Well, you will never know that with a car unless you go through every item in the car. You can, for algorithms, prove that they are correct.
But how does
Sometimes.
one day like a bug will come up or
With the car, yes. But with algorithms, mathematically pure algorithms, you can often prove that they are correct. But that is a discipline of mathematics. Okay. But you must be aware that just doing something once and it works fine is not a proof. That is what I want you to bring on board. Just because you went and bought some homeopathic treatment and you had flu and you got better, does not mean that the homeopathic rubbish treats flu. Okay. Because hitting water against a horsehide sofa does not make magical treatment. Okay, just because it happens happened, your flu could have cured by itself. So I'm saying this proof is a lot harder than just things working well once. If, however, the algorithm breaks the very first time, it doesn't work on one example, have you shown that it doesn't work? Yes. That's the weight, the burden of science, is that one counterexample will kill your theory, but a million true examples still haven't proved it. So, evolution, people still think that they can say that it's false, even though there are a million examples to show that it works and that it's a true theory. Okay, because you cannot prove something like evolution is true. You can show that it will work with a model situation, fruit flies or something, but to prove it in the general case is extremely hard to do. So one counterexample will defeat a theory, but a million true examples still have not proved it. And people who are obsessed with the idea of proof often go into mathematics, because in that pure, beautiful universe, you can prove things to be true. Yes? Yes. Yeah, no, okay. It was a little bit of a red herring, evolution.
I'm just saying, even like this, this is not kind of
Well, I have defined my system.
Yeah.
I can quite clearly define the system here. We can have a great discussion there, and I would love to chat, but it's going to derail the lecture too long. I know that saying the word evolution is like a red rag to a bull, but that's why I said it. But it's in evolution, if you define your system carefully, you can define it for fruit flies, for example. Yes. Questions? Not about evolution. Yes. Okay. Yes, it would it be a problem if I said let the minimum be a value less than every element in the list? Yes, because you would have to check every element in the list and find the minimum in order to do that. Okay, yes, yes. I said this, the minimum is actually quite it seems like an obvious one, but it's actually quite a subtle algorithm in some ways. Okay. Yes.
Just with this algorithm, I can see you do like the first step doing like an error check to check the list is empty.
Yes.
Like obviously there's a whole lot of other error checks, but I don't know.
Yeah, no, it's not entirely. This is a little bit of a red herring as well. I didn't have to do that. I could have just said that this, in fact, to be honest, I would probably remove that and say this only works for non-empty lists. Yes, it does open up a can of worms. You are right. Okay. Mental notes to self, remove that for next year. Okay. All right. We can have different algorithms to do the same thing. And several algorithms for solving the same problem may exist with different properties. So the classic example here, and some people said with the maximum and minimum, arrange them in increasing order. That's a harder problem, okay, called sorting. And sorting is quite easy to understand. You would have it basically if you've got a hand of cards and you need to sort them into order, okay. So the input is a hand of cards, however big, 5, 7 cards. Playing Texas Hold'em, when you put on the table. I've taught my kids to play poker at age 6, but all the mathematics. It's great. Your parents are very disapproving of you say it's all the mathematics. Yes, that's really good. So the input is a hand of cards and the output is a sorted hand of cards. So the algorithm is how you do this step by step. And there are very many ways to sort a hand of cards. Okay. One general method is to take the lowest card, okay? So you scan through it, find the minimum, and move it to the beginning. And then you scan through the rest of the cards, find the minimum, and put it next to the first one. No, this is selection sort. Selection sort. Okay, so it's got a name, the algorithm. It's called selection sort. And if you've programmed before, you will know that there are lots of algorithms. Bubble sort would be what? Looking at pairs of cards next to each other and swapping them if they're in the wrong order. And then you go through. It is one of the worst sorts that there are, but it's easy to explain. We will do sorting later. I'm just using it as an example. Okay, so if if you have a list of cards and you were doing this, you would go through, find the minimum. So are we saying that ace comes after king or before king?
After king.
Okay, so then which one's the minimum?
10.
Okay, so we're going to do this like this. Okay, so we'll move 10 to the beginning. Alright, and then which one's the next minimum?
Jack.
So we move that. You see, every time I have to scan through all of them, which if you talk about long list, it's quite a long procedure. And the next one, queen. And the next one, king. And the next one, okay. Even in this little example, as you see, that there was some slight issue because it's not very defined whether ace comes after king or at the beginning. It depends how you're playing. Is it the highest card or is it the lowest card? It depends on the game. Yeah, usually it's the highest, which is why I didn't object, but it can be either. Okay, any questions about that? So sorting is a very classic computer science problem. And there are lots of algorithms for sorting, different ones. What is the fastest one? Anyone know the name? Quick Sort, which was developed by a British guy who became a Sir, and I've forgotten his name. Anyway, beside the point. But sorting is one of the classic algorithms in computer science. People get very excited about it. I tend to find algorithms when they're not applied to something a little bit dry, but that's me. Okay. So I like to talk about sorting as something, but I like applied computer science. Okay, but to be quite dry, what is an algorithm? An algorithm is a sequence of unambiguous instructions for solving a problem. What does unambiguous mean? Sorry? One way of interpreting it. What? Yes. Yeah, there's one and two. Ambiguous means multiple meanings, multiple ways of thinking about it. But unambiguous means that you can only interpret it one way. English is usually ambiguous, which is why we have jokes. Yeah. And for obtaining a required output for any legitimate input in a finite amount of time. So you're not saying quickly, you're saying eventually. Okay, you do not have to implement it in software, and it's not an answer, but a method for getting an answer. Okay, so if I'd ask for an algorithm to sort numbers, for example, this list, and you tell me how to sort this list, it will be wrong in the test. Okay, it's a general method, not how do I do it in this case. Okay. You need to specify the range of inputs carefully. Full name is again, I'm very bad with names, so I keep asking. Yes, Darren. Darren mentioned that it would have been easier if I hadn't talked about the error message. What he was really saying is that I should define the range of inputs to be non-empty lists. Lists with at least one element. And that would have been easier to define the algorithm, and the error checking would have been left for the implementation. So error checking, when you're writing an algorithm, is often making sure that your inputs you're getting are the right ones. So if someone tells you to sort hamsters and your algorithm only does numbers, you need to chuck up the hamsters. So, and we saw in the algorithm that we have sequence. Each step in the algorithm was followed by another step. And you start at the beginning and you stop at the end. Okay? Except when there's a selection. If this is true, then do that. That's a selection. All programming languages support selection or iteration. And any language with these three constructs can express any classical algorithm. So when you're asking me which language, why are we teaching Python? A good answer from Gary that I got is because it begins with P. It doesn't matter. As computer science department, we do not say we love C++ and not other languages. We don't care. It doesn't matter. We expect at the end of honors, you get given they say you want to program this in Haskell, you go learn Haskell in a day. Okay, and program. Seriously. We don't care which language it is. That's why it's computer science and not just a college course where you just learn how to program in Java. You're meant to be computer scientists who can solve problems in any language if you need to. Okay. And algorithm in computer science is used specifically for a problem-solving method that is suitable for implementation in a computer program. Okay, and I'm sure you're getting a bit sort of bored now. I haven't forgotten what day it is. So we'll talk about another algorithm. Okay, this is from a recent edition of The Economist. More everyday algorithms, internet dating is extremely popular. The internet is a new matchmaker. The question is, have people tested this? Is it any better? Okay. The promises that these internet dating sites make is that you have a vastly greater choice of potential partners and a scientifically proven way of matching suitable people together, an algorithm that they use. They get some descriptions of what you've said about yourself and they try and match it to other people in the database and throw out potential mates. Okay. So this is from the Modern Matchmakers, The Economist magazine, but they're actually citing original research. So they claim to match people with compatible personality traits, and that will make people happier. Okay, however, none of the algorithms have undergone any rigorous testing at all. You pay them money to match you up, and there's no proof that they do any better than the usual way. Meeting people when you go hiking, playing computer games, not. Okay. A team of psychologists led by Eli Finkel of the Northwestern University in Illinois reviewed studies carried out by groups of psychologists. So they did a meta-study where they looked at a whole lot of other studies of internet dating sites, particularly Match.com. Okay, this is published in this journal, Psychological Science in the Public Interest. And they say many algorithms make the faulty assumption that people know ahead of the time what they want. Okay, that you know who a good match would be. You have specifications, you have a list. But data suggests that people are not good at knowing what they want. And if you actually look ahead of the time and ask people to say what they're looking for in a partner, who they actually end up with is not actually matched at all with their specifications. Okay, and they also say the very volume of alternatives may be a problem. I make a great effort, having read this research, to limit my choices in anything. Because it's well known that people, if you have to choose more than between 3 and 10 items, we're very bad at doing it. If we've got 3 things to choose from, 3 brands of washing powder, 3 types of chocolate, we're very good. But once it gets beyond 10, or really often beyond 5, we start actually being overwhelmed by the choice, and often they find in places like Pick and Pay, if there are like more than 10 jams on display, people will stop buying jam. They don't actually just don't want to make a choice. It's stressful. Okay. So it's not necessarily a good idea to have all these thousands of potential partners. And it shows that people, when they have thousands of potential choices, they make lazy, bad choices. They start looking at physical appearance to the exclusion of anything else. Don't worry about whether he's funny, but whether he looks mysterious. Okay. And of course you can't taste anyone's cooking on the web either. People tend to make bad choices. And so there's no proof. They say that maybe, if they're being generous in the analysis, that these dating sites maybe improve your chances of finding a good mate by 0.05%, which is not so bad. So they're not any better, but it's kind of fun for Valentine's Day. Any questions? No? Okay. Back to programs. So what is a program? A program is a detailed, step-by-step way, a set of instructions telling the computer exactly what to do. So a program is really an algorithm for a computer. It's detailed, it's step-by-step, and it tells the computer what to do. So the program corresponds to the algorithm that solves the problem. So your first step, if you wanted to solve a problem on the computer, is you write out the algorithm, or at least think it out. Unless you're a very good, very experienced programmer. And in general, even then, it will be better to spend some more time thinking and avoiding some errors before you do what they call cowboy coding. Diving and start coding. Okay. So programs are written in a very precise language called a programming language. And that's what we're going to teach you, the programming language called Python. Okay, so you have a problem that you want to solve, which is the minimum in this list. You write an algorithm, and then you implement that on the computer as a program. The computer runs the program with various input and produces output. Okay. There is a very classic first algorithm that we get people to write. Well, it's the algorithm that you compare different languages with. The say hello algorithm. The first algorithm you often teach little kiddies. Say hello. Okay. So, yes. Question. Oh, you're just waving. Okay. Say hello. All right. So how do I do this in Java? It's popped up on the wrong screen. Okay. So I'm going to do this just for fun on the command line interface, and that's Pascal. Python 3, so I'm running Python. And how do I say hello? Right. That's the hello world. It's usually hello world. Hello world. Okay, so that's my first program that I've written for you. Okay. But it's the classic, when you're explaining a new programming language to someone, the first thing you explain is how to do hello world. And the reason, one of the reasons we're doing Python, for those of you who keep asking me, is the difference in hello world in Java, C++, and Python. Okay. So Java, what? Not syntax errors, just syntax. Yeah, okay. Let's just tone it down a bit. In Java, this is a comment. So I've got comments in all of them. They're different in different languages. Class hello world, open bracket, static public void main, string args, open bracket, close bracket, open close bracket, curly braces, system.out, the print line, hello world, close bracket, semicolon, if you forget that you're dead, close this bracket, and close that bracket. Okay, if you forget any of those, you are dead. So, immense pain when you first start programming, because you have not yet got this bracket spotting module which you develop after years of pain. I can spot a missing bracket very quickly. Okay. So that's only after I actually quit computer science in second year in frustration about a missing semicolon and came back to it because I missed it. Okay. So, this is hello world in C++. Hash include iostream.h. That's not a comment, you have to put that there. Main, and then you could usually put other stuff in the main. C out hello world, end line, return 0. And hello world in Python. This is a comment, print hello world. Okay, that is really one of the most compelling reasons we are teaching you Python. Besides the fact that all the physicists and mathematicians have moved to Python, and that it's a lot faster than it used to be now, and that Mark Shuttleworth made most of his fortune from programming Python. That's no semicolons, easy to see what you do. Syntactical junk has been moved. Syntaxes of the words is the way you have to write. Okay. So, Python combines remarkable power with very clean, simple, and compact syntax. You don't have to put all these other things. We can teach you Java because Java has a lot of other advantages too. But as a first programming language, Python is great. Questions? Complaints? Yes?
Is this entire PowerPoint on Ruler?
Yes, I need to update it with the, maybe, with the Valentine's Day stuff. Maybe, we'll see. But yes, it's. I usually put up slides after the lecture, not before, because I do change things. Okay, often during the lecture, and then it's a pain. You don't know which version you have, so I'll put it up after. Okay, so now just to sort of finish our discussion of algorithms, why are they so important? Why am I going on about algorithms all the time? Algorithmics is more than a branch of computer science. It is the core of computer science, and in all fairness can be said to be relevant to most of science, business, and technology. Okay, that's David Harrell, who wrote a book. Okay, why are algorithms so important? A person well trained in computer science knows how to deal with algorithms, how to construct them, manipulate them, understand them, analyze them. This knowledge prepares him for more than writing good computer programs. It is a general purpose mental tool. We are training your brain, which will be a definite aid to his understanding of other subjects. That's the his, her, his. Okay. Whether they be chemistry, linguistics, or music, etc. The reasons for this may be understood in the following way. It has often been said that a person does not really understand something until he teaches it to someone else. Which is why those of you who've done programming before would be could well occupy your time trying to help your classmates. Because the person who learns most in this room is who?
The teacher.
Me, yes. I learn the most. It's been proved from teaching. It is the best way to learn. Because when you're teaching, there's always someone who asks you that question on that slightly fuzzy bit that you've been glossing over for years. You're like, okay, that's a good question. And then you sort it out. Yes.
And it's also that when you learn something, you learn one part. When you teach something, you need to learn a million parts.
Yes, you really understand something when you teach it. So I do recommend forming study groups and teaching. You know, do some community service if you've programmed before. You will benefit more than anyone else. Okay. So it's often been said that a person does not really understand something until he teaches it to someone else. But actually a person does not really understand something until after teaching it to a computer. The most stupid entity in the room. Express it as an algorithm. You have to tell the computer exactly. No fuzziness there. It will do. When it's doing something wrong, it's because you said it. Okay. So, why should I care what Donald Knuth says? You just say something clever. Okay. He is Mr. Algorithm. Okay. Donald Knuth, Professor Emeritus. We discussed what emeritus means. He retired early. He did so much good stuff. Of the art of computer programming at Stanford University, which is extremely highly rated worldwide, Stanford. Okay, it's a seminal multi-volume work. I think he's working on volume 5 at the moment. Okay. Yes, it's there. And he's been called the father of analysis of algorithms, analyzing algorithms, stepping back and proving whether they do what they should do. He also is my hero because from January the 1st, 1990, he said, I don't have an email address anymore. Everyone has to mail. Snail mail. Okay, because he's not getting any work done. And my tip to you guys is don't open your email when you sit down to work. Spend an hour doing some big important thing and then open your email because it really is a time sink. It just, all your time disappears and you think you're busy, but you're not busy effectively. Okay, so that's Donald Knuth. And that is how you pronounce his name. You can look it up on the web. Okay, so the limits of algorithms. Algorithms can't do everything. There are problems for which no one has yet found an algorithm. They may claim that they found an algorithm to match people, but they haven't really. Okay. There are algorithms. There are problems for which there are algorithms, but they take too much time. And there are problems where it has been proved that you can't ever find an algorithm to solve it. It is provably unsolvable. Okay. A good example of algorithms that take too much time are the Tales of Hanoi. Has anyone seen that film, Beginning of the Planets of the Apes?
Rise of the Planets of the Apes.
Rise of the Planets of the Apes, where the poor chimps are doing. They're actually doing. They call it some other name in the film, which is actually a bit of a cheat. It's called Tales of Hanoi. It's a classic programming problem. Okay. And Tales of Hanoi is solvable, but the algorithm, if you use it, it's basically how do you move the disks from one peg to another peg without ever putting a bigger disk on top of a smaller disk. It's a nice algorithm to look up, very classic one. There's a solution, but as soon as you have more, say 10 disks, the algorithm takes too much time. From 100 disks, you can't solve it. So it will run too long. We'll talk about these things really a lot in third year with the theory of algorithms. And the halting problem has been proved that you can't ever find an algorithm to solve it. The halting problem is a problem that, given any program, can another program algorithm tell me whether that program stops or not? Does it run forever or does it stop? That's the halting problem. Quite simple. So your little algorithm is meant to say, take as input another program and say, will that program ever stop? Does it run forever or will it stop, finish in finite amounts of time? That problem is provably unsolved. And the person who proved it is called Alan Turing, and if you're finding or interested in this, please look it up, the halting problem. Alan Turing, who was a very, very famous early computer scientist who had a very tough life. Very, very bright guy, also homosexual. And the British government discovered that he had his apartment robbed by his current boyfriend. Went to report it to the police. He'd done a huge amount of work for the British during code cracking in the war, Second World War. When he reported to the police, they weren't actually interested in the theft. They prosecuted him because it was illegal in those days to be homosexual, and forced him to take estrogen, which is a female hormone. Which made him grow breasts and get very depressed, and he committed suicide by eating a poisoned apple. So very sad. Very, very brilliant guy. Okay. Another interesting tidbit before you go. Algorithm is a Persian word named after a famous Persian mathematician in the 9th century. Does anyone want to try to pronounce that? Muhammad ibn Musa al-Khwarizmi. I'm probably doing it very wrong. But algorithm comes from the title of his book, Al-Kitab whatever. But from algebra is derived. Okay, algorithm comes from a Latinate form of his name. And he did some amazing things like introducing Hindu-Arabic numerals and algebra into European mathematics. Okay, and the last thing for those of you who are bored, you can look it up if they're on the slides. I want to know the answers to this. The answers are not on the slides. Okay, so checkpoint, which of these are an algorithm?